To the end of the conference. I'm Christine Simpson. I'm here at the Agora meeting as a member of the ENSO collaboration, but I'm going to be talking today about a project I've been doing with a different code, the Arepo code, which is a moving mesh code. This is work I'm doing in collaboration with Volker Springel, Rudiger Packmore, Federico Marinacci, and others. Simon Glover among them. And I guess whenever I tell people that I'm a postdoc at HITS, the first question is, what is HITS? So Heidelberg has many institutes, so we're one of many, but we're sort of new, so not that many people know who we are or where we are. So MPIA is here at the top of the Königstuhl, and we're sort of partway down on the same level as the castle, which is very picturesque. This is HITS, and so we're a theoretical science institute, so we're not just astronomers, we're also biologists, linguists, and others. So currently we have two astrophysics groups, the Galaxies group led by Volker, and then we just hired a new group working on supernovae, led by Fritz Ripke. So we're now we have 20 or so astronomers at HITS, so we're definitely growing. But so today I'm going to be talking about feedback in galaxy simulations, like every galaxy simulation talk at this meeting. But just to reiterate, why is this such a difficult problem, and why have we spent so much time and energy on it? Well, I mean, we think that stellar feedback plays an important role in shaping galaxy properties and evolution. And it's a hard problem because you have processes that are being generated on scales of stars, of H2 regions, of supernova remnants that are, parsecs to tens of parsecs in size. We think they're playing a role in generating galactic scale winds, which are tens to 100 kiloparsecs, and then are playing a role in polluting and shaping the CGM, intercluster medium, and the intergalactic medium. And even if you had the resolution to resolve all of these scales and the coupling between all of these scales, it's still not clear what you mean when you say stellar feedback, right? Because there's a lot of things that go into it. There's thermal heating, there's kinetic winds, there's radiation that both ionizes and perhaps exerts pressure. Also cosmic rays, which might also play a role, especially in driving winds. And there's been a lot of work, despite these challenges, a lot of good work on tackling these issues in galaxy simulations. So there's been sort of two approaches that I think are interesting to highlight, and one is that if you just say, well, we don't resolve the small scales, so we're just going to create something, a phenomenological wind, and we're going to just treat the ISM with just a pressurized medium where you imposed a stiff equation of state, where you're basically just abstracting over a lot of the small scale part of this process, right? Of course, this has, you've been able to apply this to very large volumes, such as in the Illustrious simulation, but of course it has limitations, if you want to understand how winds entrain material as they come out of galaxies, this kind of model can't really help you. However, recently, a number of groups have been reaching resolutions where you can start to hopefully resolve the coupling between some of these scales. So we heard a lot from the FIRE collaboration. This is a plot of their halo mass, stellar mass plot. Also, in Ramses, there's been a lot of good work. We're sort of reaching a point where we're hopefully going to be able to bridge this scale of the very, very small scale processes generating these large scale effects on large objects like galaxies. And I think we should also keep in mind there's another simulations community that's also working on the other end of this problem of star formation. And in that community, I think people are now starting to think a bit about galactic environment in the formation of molecular clouds. And this is some very nice work by Rowan Smith where she is simulating the formation of molecular clouds in a little wedge of a galaxy where they have imposed a potential for the spiral arms, and she's trying to understand how clouds form in this potential. You get these sort of fingers, et cetera, and what chemical composition you get. So with this in mind, I'm going to be talking today about some simulations I've done of feedback in a stratified box, which if you can just picture, you have a galactic disk, and I'm just simulating a column passing through this disk. In these simulations, I'm assuming that at first I'm going to show you models where I assume a global star formation rate just based on the surface density of the gas. And I'm assuming that supernovae go off in proportion to the star formation rate and are injected stochastically. We also have a model for non-equilibrium molecular cooling, and we have an interstellar radiation field that is attenuated by some gas self-shielding prescription. And so this is showing you the box. It starts out in isothermal equilibrium, but this is showing you one example of what it looks like after, I think, 20 or 30 mega years after the start of the simulation, where your central disk starts to get holes blown in it, and you start to get material coming off the disk. This is only the central 5 kiloparsecs or so. So just to remind you, these simulations are being done with the Arepo code, which is a bit different from other hydrodynamic codes used in astrophysics. It's fundamentally Eulerian in the sense that you are discretizing volume and you are computing fluxes between volume elements, and that is how you're updating the fluid motion. However, your mesh can deform. This is showing you a Kelvin-Helmholtz instability where you have a shearing flow, and you can see instabilities forming on the edges of this flow, and over time you get these nice rolls. And if you had sort of a Cartesian mesh code, you would start to get artificial diffusion in these rolls. They wouldn't be as well defined. So it has some of the advantages of an Eulerian code, but also some of the advantages of a Lagrangian code. And so to date, this code has been used in galaxy formation using the sort of wind model that I described at the beginning, where you just assume galaxies that have a certain star formation rate launch winds with certain properties, which you can play with. And this is one example, some models of the Aquarius halos run by Federico Marinacci. And you can study things about, say this was a paper about the CGM, like what do you expect for column densities of gas around a Milky Way type halo. But you really can't explore the launching mechanisms of winds, right? It's just not designed for that. So this is sort of the first attempt with Arepo to try and simulate some of these processes. And so the first result I'll highlight is just, we played around with the placement of supernova explosions. So, this has been done a lot in the ISM community. And we sort of reproduce their results basically in that, if you place the supernovae, so we are assuming in both of these simulations, this is showing you density projections after 20 mega years, we're assuming the same star formation rate and the same supernova rate in both simulations. However, in the one on the left, we're placing the explosions in high density regions. And in the right-hand panel, we're placing them randomly. And I say randomly, they're random in X and Y, and then they're more concentrated towards the center, but they're not explicitly going to be centered on cells that are the highest density cells. And sort of unsurprisingly, the random placement is more effective in driving a wind. This is just showing you the mass loss from the volume over time. You basically don't lose any mass in the peak driving case, but you do start to lose some mass, and this will continue down in the random driving case. If you then look at the porosity of the medium, so the fraction of the volume covered by hot gas, in the peak driving case, you sort of equilibrate to something that is, 1% or so, but in the random driving case, you jump rapidly and you plateau to a much higher value. So your medium is much more porous. Okay, so this is all well and good. However, supernovae are not random in the ISM. So we would like to sort of come to a model that's a bit more physically tied to the state of the gas. So here I'll show you a model where we compute a star formation rate cell by cell, assume based on the local freefall time of the gas and an efficiency that we assume 1%. And so in this model, I guess I'll just let it start looping. This model does not drive a wind in the way the random driving one does. However, it does maintain the gas scale height in a way that the other two models don't, that have a fixed global star formation rate. So this is showing you the height that contains half the mass in the volume, and the purple is the self-regulating model, and then the red is the random driving, and then the orange is the peak driving, but with the same star formation rate. This is the star formation rate, so we have fixed it to be flat in these two cases, whereas it can vary globally in the second case. And as you can see, over time, the scale height, like as the scale height collapses, the star formation rate will go up, and it will self-regulate over time. However, you're still not driving a wind. So the question is, what physics do we need to include to do this? And this is still a work in progress. We're still putting in physics, but I should just mention that one of the things I found very interesting at this meeting is there's been a lot of discussion of feedback processes and what do they do in galaxies. And I think for a long time we've sort of had this, I guess, the bathtub model, which sort of assumes that what regulates winds, winds regulate star formation. So the amount of gas you have in the bathtub is what determines your star formation rate. And I guess I think there's a lot of hints now, especially on the dwarf scale, and there's a lot of interesting simulation work suggesting that this doesn't need to be the case, and that the physical processes that regulate winds need not be the same physical processes that regulate star formation. And so there, John Forbes had a very nice talk, and I mean, there's been other works on, say, cosmic rays, and even just ionization feedback could be quite important. And so, when we construct these subgrid recipes that we're applying in these large-scale cosmological simulations, we really do need a detailed understanding of these physical processes on these small scales in order to put in something that behaves in the correct way on a macroscopic scale. So I guess I will just sort of conclude here and mention the future of this project. So we currently have tests with MHD running, so that is coming. Also, we're planning on much higher resolution simulations. So the ones I showed you had a target gas mass of 10 solar masses. I think 1 or even 0.1 will be certainly possible. In addition, we'd like to play with additional physics, such as ionization feedback and also cosmic rays. And this is a plot that I wanted to highlight. So we think cosmic rays are generated in the ISM in shocks in supernova remnants. And so this is showing you a thin projection through the midplane of one of our runs. And this is showing the Mach number of the gas. So potentially these are all regions that could seed cosmic ray formation. And so we would potentially like to explore this in future runs where we could seed cosmic rays in these bubbles or along the shock fronts. And that could be an important physical driver in generating winds. And then I guess also we would like to do some runs with star particle formation. And I mean, we've already done some of those, and I didn't have time to focus on that, but this is just showing you a plot of the porosity of the medium and a coarser resolution run for much longer time, where we create star particles and then we delay the supernovae created by each particle by 0, 1, and 5 megayears. And as you increase the delay time, the dotted one is the 5 megayear delay time, you're getting closer and closer to something that was like the random driving case, right? However, the piece that's missing is that presumably in the intervening 5 megayears, the star particle should have created a little H2 region, should have ionized some patch of the galaxy, and that should couple with the supernovae once it goes off, and you probably then won't look necessarily like the random driving case. But that is in the future, and that is coming, so I'll thank you for your attention and take any questions. Thank you.
For a couple of questions for Christine.
So awesome controlled study. Always happy to see more controlled studies. I'm just curious if you've looked into any issues with resolution when it comes to actually venting the winds. I've seen in some of my little tests like this, and there's a really good paper from Martin Stringer a couple years ago that showed that as you go to worse resolution, numerical viscosity makes it harder and harder for winds to actually leave the disk. So have you tried, say, just running the same box at a higher or a lower resolution and seeing if the outflow rates change?
I mean, I've run the sort of strong feedback, the random driving at 110 and 1 solar mass per cell, and they seem to pretty much converge. So I mean, of course, we can increase in resolution more. I guess the issue is, like, one thing is we want to move towards having star particles. And as you go to higher and higher resolution, your star particles have to get really small, or you have to sort of do, make them from clumps, which is the next sort of thing that's on my list to do. So, yes.
Can you say more about how your 10 to the 51 ergs gets injected?
Okay.
What Volker has done in the past is inject thermally, which makes sense if your resolution is terrible, because it'll thermalize on some big scale.
Yep.
You're trying to run at high resolution, and it makes no sense to inject the energy thermally, and moreover, it makes no sense to ignore the energy that's put in by the O stars, which greatly exceeds the energy of the supernovae. If you don't put that in, then you're missing the part that's, whenever you look at these things like the Rosette Nebula that people have shown several times, you see that the O stars have really cleaned out a large region.
Yes.
And that's, of course, crucial to set up the initial conditions for when those stars eventually supernova. If you're not including that physics, then you're not putting the momentum in, which is going to generate the pressure, which is going to generate the winds. So how are you putting the energy in?
Okay, so I guess there's 2 questions to that. One is, how are we doing the supernova feedback itself? And 2, why are we not doing, why are we not creating H2 regions before the supernovae? So to the first point, yes, of course, right. So to the first question, I've implemented a scheme very similar to one I put into ENSO, where you are able to put in kinetic energy with net zero momentum, right? So you have these explosions that point outwards, and I've done tests. So everything I showed was purely thermal. I just wanted to show something that was very controlled and simple for the talk. But when you have a situation with the strong feedback where the porosity of the medium goes to basically it's all filled by hot gas, it doesn't really matter, because your density is just so low. It's such a hot rarefied medium. It doesn't matter if it's thermal or kinetic. If you're in one of these cases where you have sort of a more, flocculent medium, yes, then it does matter. So I've done tests where I've injected 30% of the supernova feedback in kinetic form, so divided the total energy budget of the 51 ergs between the two, and yes, that does make a small difference, yes. So as to your second question about H2 regions, like that's certainly in the plans. You know, we're getting going on this project, and hopefully we'll have something that you would find very interesting soon. So, okay.
All right, let's thank Christine.
Thank you.
So we have a